So this is part of the Epics training sessions that Nick and Andrew have put together. It's a great thing to teach everybody, the BMON scientists and the staff, about Epics. So I'm going to talk to you about using Python with Epics and the PyEpics library. This is channel access clients, not trying to do anything fancy with the server end. Why? OK, so Epics channel access and Python. So why would you want to use Python? I think that for most of you, this is not a real open question. Basically, Python has a lot of advantages as a scripting language for scientists to use. And a lot of scientists around the ring and at other sources and in other scientific domains are already using it for lots of stuff. So there's lots of libraries available. And it's a good high-level language with object orientation to use for both scripting of data acquisition and data analysis. There's lots of libraries to use. So using it from channel access to get your data to then feed into some other application is highly, highly valuable. So PyEpics has sort of 3 levels, or maybe even 4 levels of how you can access the channel access library. I should say, starting, if you don't know anything about Python and you don't know anything about Epics, this lecture might be kind of a little obtuse. So channel access allows you to get information about network resources that handle Epics process variables. So the lowest level is just to use the C library directly. So you can, with Python, just go to a C DLL or DLL and open it and just use its methods, and you get at its data. So you could use it that way. That's much too hard to use because the channel access library has complex data types, C structures, and a lot of functions that you need to handle, including like handling pointers and so on. And that's challenging to do from within, but it's challenging to do in everyday use. So on top of that, there's a C-like API that's written that wraps that lowest level, the libca. And this gives an interface that's very much like the C channel access library. The function calls are nearly the same names, and they're nearly the same behaviors. There's some things that you don't need to do in Python that you need to do in C, like handling different data types and so on. So that's handled for you in this. And this supports all the callbacks for all the kinds of callbacks that are used frequently in channel access, events and gets and put callbacks and so on. This is built on top of the libca library, so just the C channel access DLLs, and the C types library that comes with Python. So that means that it's all built in and it's easy to do, no extra libraries. Then on top of that layer, the simplest channel access layer, there are PV objects, which are objects that represent a process variable. These have methods and attributes that go with them. They're Python objects, so they're fully object-oriented. And you can do things like a get method and a put method, or get its value, and all of its other kinds of data. And these are automatically handled connection and event handling, and they extend the data types. And this is then built on top of this layer. And then finally, there is a simple procedural layer that just provides functions, CA get and CA put, and so on, that are built on top of PV objects. So this is the simplest interface to use. And these are then very much like the command line tool, CA get, CA put, CA monitor, and so on, that are useful from command lines. And you can use them inside of a Python script as well as the command line. And then there are higher level objects, devices and alarms and so on, and GUIs that I'll show you that are also built on top of the PV object. So there's all of these layers here, and what mostly you're going to want to use is either the PV objects or the procedural interface, the procedural functions. In fact, these procedural interfaces, so the CA get and the CA put function, are really so these do like 90% of what you need, maybe 80, 90% of what you need. So if this is new to you and you walk away with this screen, you can do a lot of stuff, right? Because you can do a CA put and a CA put and a CA get. So you can go to any motor or anything and you can get its value, you can print its value, and you can move things and set values. So there's a couple of options with this that aren't in the normal command line tools. Like you can get a process variable name as a string. And this returns either a nicely printed, a nicely formatted version of the value, or for enum types and so on, it'll return the enumerated string. So that's better to read. And with put, there's the most important option in CA put is to wait. And wait equals true means that this put will wait until the processing completely finishes. So that could take a very long time. If a motor is moving, it waits for it can take a long time. And there is a timeout option to say to wait no longer than some specified time. With using these functions is actually pretty efficient, because when you do a CA get, first it creates a PV, stores that, and then the next time you access that PV, it uses the stored PV. So so unlike the command line version or in C, that is not making a new channel connection every time for each of these gets with the same PV names. There's also CA info, which shows you the status information and control fields, so all of the status and control limits and the timestamps and what the host is and so on for a PV. And then there's a monitor function, which is pretty simple. It just prints out the value as you go. So you say CA monitor, and it immediately starts printing out values as they update. And you have to do CA monitor clear. So you can modify this. You can give a function to intercept that data and so on. But it really, if you're doing this, you'll want to use PV objects, which I'll get to in a second. But that's available. It's very much like the command line tools. OK, let's go on. I should say also that if you have any questions while this is going on, you can interrupt me and make comments, questions, rude comments. OK. So PV objects are the recommended way to interact with a process variable. And the main reason for that is that they have automatic connection management, and they automatically monitor the values. So they set up internally an event callback so that when you get a value, it's already received the latest value. So they're not quite lightweight objects. They have a lot of information in them, but they're definitely the convenient way to really interact with process variables. So here you just create one with its name, and then you can immediately print it, and it will even tell you what the count, type, and what the access is. And you can also get stuff like its host and control limits. You can get the value, or you can use the value either get and put methods, or you can read and write to the value attribute. So you can either say get or PV value or PV1.value, and it does the same thing. It returns. What that really does is return the last value that it received from a monitor, from a change. So the most recent value. Get also has the as string equals true option. So if you do that, it will format it according to the precision of that PV and give a nice string representation of the value. And there are many attributes. Some are listed here. There's many more attributes like listed in the info, CA info for all of this other control limits and control parameters for the PV. Again, PVs are set up to be monitored internally and asynchronously. That means that the value might change between one call and the next, and you won't necessarily know that it's changed until you ask for the next value. You can ask to be told when the value is changed. I'll get to that in a second. And get simply returns the latest value that the PV received. So a few more things on get and put. So get for enum strings also can get its actual value or the list of enum strings, all of the state names, and you can get as string, and that will return the string representation. And put, again, the put method for a PV, like CA put function, can take a wait equals true, and that will also wait for completion of that PV. So if that's a motor, it'll wait until that motor is done. And if it's a detector, it'll wait until the data has been acquired. OK, so still, things are monitored internally, but you may want to get a notification of the change of a value. So you may want to say, when a value changes, let me know and do this, do something with that value. And here you can add a callback. So here we can create a PV of some unknown name and add a callback, which is this function here. And then you can just wait, so wait for 60 seconds, and then clear all the callbacks. And that will, if that value changes at any time during those 60 seconds, it will run this function and print out the values. So you're asking, when you add a callback, you're asking for the internal library to call some function. So it's important that the function have arguments that are expected. And the way to do that with Python is to make sure that is to give keyword arguments and make sure that you use the ** keyword arguments to say stuff all of the other keywords into this arguments into this dictionary. Because there's a lot of things that it's going to pass back. It's going to pass back all of these and actually many other things. It might pass back limits and units. In fact, it's kind of undetermined what it'll pass back until the PV is already monitoring. So you should definitely use the keywords arguments, but then you'll get all of these different values. You'll get the PV name and the character value. That's the character representation of the value, the as string representation. And you'll get the count and the field type as well, and the numerical value if there is one. So I said this happens. Here we're not telling it when to call this. We're just saying create this PV, add a callback, and then wait for 60 seconds for things to change and for that to be called. So the internal CA library is calling your callback function that you defined, and it's calling it asynchronously. So there's some things that you have to be aware of that you have to be kind of careful with that have messed people up in the past. Basically, your function runs inside of CA pend event. If you've been following this course, that's been discussed in previous courses. So that's the polling loop that the CA, that's the polling time that the CA event loop takes. So you can read values for other PVs inside of an event, inside of that function, but you can't really do other I/O inside of that function because you're in the function that's processing events. So the things you can't do inside of a callback are the things that you might want to do that you can't do, is you can't really put a new value. It's not that it's not allowed, it just doesn't work because there's still I/O to be processed. So the recommendations are to keep the callback function small and fast. So don't say when a value changes, go calculate the FFT of it and then plot that to a function and then write that to disk and then send email. Just notify that. Just note that it's changed, and then in your code later on, if that's changed, then react to it. So back in this loop, you would change this wait to set a flag here. This PV has changed, and then in your while loop, you'd sleep for a little while, wait for events to happen, and then act on those events, those changes after the notification has come in. I'm going the wrong way, aren't I? I'm still going the wrong way. OK, sorry. OK. This issue is especially profound in GUI codes, or it can be potentially profound in GUI codes, because there, not only is channel access running an event loop, but the GUI is running an event loop. And those two event loops have to agree that things are happening, when things are happening. So you may want to say, when this PV changes, I want this value on a screen to update. Or you might say, when I push this button, I want this motor to move. And for both of those, you have to be a little bit careful in doing that and what your callbacks can do. It turns out that PyQt, PySide, and TK seem to handle this issue well itself. They actually internally say on event of a GUI event, wait until that process is done, and then hand that off to the other C++ codes. With wxPython, you have to be more careful, but PyEpics includes ways to handle this efficiently and without causing crashes. Okay. So one of the things that we use at the Beamlines a lot that are somewhat challenging for many Epics applications are waveform records. So for array data. So with Python, what you'd want to do for that, or for scientific Python uses, you want to turn that into a NumPy array. And PyEpics by default, does that automatically if NumPy is available, which it is for most systems and all of the ones at the APS. So here you can create a NumPy array and just put that NumPy array into your PV that is accepting a waveform. So the scan record positioner arrays, for example, you can put an array of values in there like that, or you can get the array values and get a limited slice of the array values. For character waveforms, array values and waveforms are especially useful because you can use character byte arrays for long strings, which is a challenge with Epics, that the limitation on most strings is 40 characters, or at least it has been. And sometimes, many times for file names and so on, you need a longer string than that. So you can use a character waveform. So many of the area detector file plugin handlers use these, and you can just then either get that gives you an array of the bytes. That spells this string. And you can also get it as a string again. And then you can also put just a string value, and it will just put those characters into the waveform. That obviously means a couple of things. First of all, it means like ASCII characters, not Unicode. And it means that you have to be careful about if you want zeros or nulls in your character string. So this is definitely treating a byte array as a character string, which is, but that's a very convenient way for using area detector plugins to be able to just put that folder name into your with a string. Okay. I have a couple slides that I'm just going to talk about the lower level, the CA module, just because it's important. This has some implications for understanding how the PVs work. So here with the channel access library, you create a channel that gives you a channel ID, and you can work with that, getting the field type and so on. And you can also then do puts, but instead of using the PV name or the PV object with the CA put function or the PV objects, here you need to use that channel ID as basically the identifier of the channel. That is the identifier of the channel. And you can also, so this also allows you to do things like put with await and set up a callback for events. And here it's create subscription, which is channel ID, and then this function. And that works very similar to the way PV objects work. So if you want to use this lower level, if you're more familiar with the C code, this is a fine way to go. And there are many slight changes from C to Python for this library. So for example, the names are put in a module instead of having the CA underscore, and some things just aren't required in Python that are required in C, like handling different kinds of data type and allocating memory. One thing I'll talk about in a second or in a little while is threads. And here, within Python, we tend to use a single thread context for channel access. Okay, and also the initialization and the finalization of the channel access library is handled for you automatically. So you'll notice that in these examples, I just created a PV and then immediately put to the value. And that's because when it needs to, it will initialize the channel access library. So you don't need to create a context or initialize the library. OK, so there are a few things that are different from the channel access library working just like C. There's a few small things. One is that preemptive callback, so events happening asynchronously, is on by default. You can turn this off so that you have to explicitly poll for events to happen. But I don't recommend that. Many of the things I'll show you later sort of depend on the asynchronous behavior. And the channel access library, C library, supports many data types, and not only two of them, the control and the time variant are supported within PyEpics. That's because we're not really trying to save a couple of bytes by using a little bit less memory. And waveform records are always converted to NumPy arrays if that's possible. That's both on input and output. And And some things for exception events and so on just aren't needed. I'm still going the wrong way. Also, because this is used a lot of beamlines that are using arrays, Epics CA max array bytes is set by default to 16 megabytes, unless it has already been set by your system. So getting array data will probably work if you forget to set CA max array bytes, but you might want to set it bigger than that if you're working with very large cameras. Connection and event callbacks are used internally with PVs, and you can write your own functions to be called on events as well. Right, so very large arrays do not get an event callback. So with a camera data, if you set up a camera array data or the image array data PV, that may not be monitored. You can monitor the other PVs, the image counter and so on, and then go fetch that large amount of data. And then there's what triggers an event is we made a choice on what triggers an event of event, log, and alarm. Okay, so here, just again, actually this is so mostly because some of you may be interested in this implementation, or you may want to see this as an example. So there's a CA shared object library on Linux. It's SO. Windows is CLO. And it's this easy to use that library. So with the C-types Python module. So this can be done with, so I'm showing this here as an example. This can be done with other C libraries. If you have other C libraries, you can use its functions, the functions from that C library internally. And you may have to do things like tell it that the argument's a double and so on. But it's not that hard. In fact, so channel access is probably a challenging case because the event streams have lots of complex data structures. So it's very easy to do this work. Okay, and the real advantage of using C-types and then using that to build on top of libca and building the CA on top of that and PV on that, why that matters for the beamline scientist is that it makes it very easy to port. So basically, it's pure Python code. There's no C code in the wrapper at all. It just installs everywhere. And the CA library, libca.so, that's debugged. Somebody figured out how that works. So all of that stuff works. And there might be some debugging for the Python code, but not of the C code to be done at all. This also turns out that using the C-types library gives the best possible thread support. So there's nobody from Diamond or NSLS2 here, so I will say this is the best way to do threading with Python, is using C-types. There's another Python module out there that has a different opinion. Python has, I'll talk about this in a second when threading. Python has a lock so that its interpreter is only running one thing at a time. And this handles this issue well. And it also means that both versions of Python 2 and 3 are supported with very little code, and even to the extent that Unicode in being the default in Python 3 is not a significant problem. There's one page of code that is different between Python 2 and Python 3. So threading and multiprocessing. So threads and multiprocessing are both supported, at least to some extent. I'm not an expert on threading or multiprocessing, but threading and multiprocessing both work within Python. Here you can set up a monitor. So here it's maybe hard to read. Here I've created a thread that's going to run this function, which creates a PV inside the thread, and then sets up a callback and waits for that thread to run. I'll run it once with one PV for 10 seconds, and then start another one with another PV for 3 seconds. Let them both run. They both run simultaneously. The outputs will be interleaved. It works. And you could also, it's not shown in this example, you can create a PV outside of this thread, in the main thread, and that will also interact. And then these start the processing and then wait for that to complete. But I want to be clear, because this is different than Java or C. It might be different than other things. But I think it's the same as I think it's the same as like Perl and Ruby and other scripting languages. Python doesn't really execute two instructions at once. There's an interpreter, and that's interpreting the bytecode that your code gets translated into. So it runs one instruction at a time, actually in one process and on one core. It doesn't use multi-cores. This is kind of like possibly an issue. If you use multiprocessing, you can get by with this. So it's running one thing at a time. Even in multi-threaded, it's picking which thread gets the baton of who gets to run its code. So this is called the global interpreter lock. So only one of these threads is really running Python code at a time. But at each call to C code or I/O, so any call into the C type, so any call into channel access, or any call into I/O code for print, it will allow that baton to be up for grabs, so some other thread can grab it. So that does a good job of allowing two threads to run apparently simultaneously while your I/O, which from this point of view, channel access is all I/O, happens in the background C threads that are in the underlying code. So the C processing is happening, and you're getting these to run. And I think that's the best possible route to doing multiprocessing and threading. But if anyone has a better idea, let me know. OK. Multiprocessing also works. Actually, it's slightly more complicated than this one page, but it can also be done well. It works. It works. I don't have that example. You would almost say from multiprocessing, import process, and replace it with the same thing. It's like 2 extra lines to do that. OK, so I'm going to show you a couple of things. So about halfway through. Good. I'm going to show you several devices and GUI components that are built on top of PyEpics. So let me first talk about devices, because this is like just a collection. A device is just a collection of PVs. But it's a convenient thing to use. And if you're finding yourself writing a lot of code, this can be a very helpful way to write your own higher, like next level up objects. A device just maps a set of PVs, often with the same suffix, or with the same prefix, but not necessarily, to an object. And then you can access that whole device or any of its attributes as a single thing. So here, for an analog out, for example, those are, I think, most of the fields that happen in an analog out. And so this is, or analog input, sorry. So this would just make an analog in device. And it would create PVs out of all of these components of an analog input record. With that code there. And then what you can do is you can import an AI device and then create this. So a pump would be an analog input with this PV, and you can immediately get at its description PV, which is up here someplace. It's one of these. And you can just say .desc, because that's one of the field names. And you can get the value as a string, like that, get val as a string, and get the engineering units. And that would print out this line here. You can also get out other things too, the device type and so on. It has all of these in there, and you can also get at the underlying PV if you really want access to really work with the underlying PVs. But here you can just work with that as a pump. So that's one of the key points is that this is all it took to make that. So there's already a lot of code to help you make those. So that makes it much easier to deal with multi-PV objects. You can also, when you create an object, when you create a device, you can also add methods to that. So there's a scalar device, and this has setting modes with like nice method names, like one-shot mode or count time, that will just set that. But that means that you can create a scalar, set the calculation, and enable calcs and one-shot mode and count. And that will do all of the processing for a scalar record. You can also do more complicated things in the calculation. You can do database lookups or do longer calculations. So I have an ion chamber calculation so that you read the current from an ion chamber, and you've told it what gas it has. And it looks up in the data sheet of that's a few kilobytes of data, and it calculates what the flux is in photons per second. given the energy and all these other things that go in, it'll do that calculation and put that out. And that ends up being like 100 lines of code to do that calculation. OK, so a key example of a device is a motor. A motor has like 100 fields. And it's got like a lot of things you might want to do with it. You might want to move the motor in user or dial values. You might want to check the limits and so on. So this exists as a device. Motor is a device. You can just create a motor, and you can easily get its description, its readback value. You can do a move in dial units or in user units, and so on. And you can get all of these fields, slew speed, description, and so on, as nicely formatted attribute names. And there are several devices included in the main distribution and more being written like sort of all the time. So again, for many of the things that are Epics records, especially complex records, MCA records, scalar records, scan records, having these kinds of classes that represent those is very useful for doing everyday code. There are also, so one thing, there's also an alarm class with somebody that was written to allow you to set up an alert. So you can say, you can create a PV, and then when something changes, when something goes past a trip point, you can send email or some other alert. Send a message, send a text message, send an email to a Twitter account or whatever. And you can turn off some system. So this just, at each callback, this just does a comparison of an operator, a comparison operator, and a trip point. And then it will set that, run that code when that happens. Let's see what else. So actually, based on that, and I'd like to show you, so now I'm going to show you some applications that have been built with PyEpics. Some of these are to show you what can be done, and some of these are to show you what you might be actually interested in using yourself, or give you ideas of the kinds of things that can be done. So we have a data archiver that's using wxPython and MySQL and a web page through Apache, and we find this very useful, and it's a bit of a pain to set up, and it's a little old in its formatting and Outlook, but this might be the kind of thing you want at your Beamline. It gives you a web page, so accessible from outside anywhere without a VPN connection, to look at PVs that you decided you want to look at, and you can make a tab display to isolate any of those values. And then when you click on any of these values, you get the plot of the by default last day, and you can then set what the time range is for those values. So you can look at motors, positions, motor offsets, pump speeds, and so on, and you can get these plots. And this is just so useful for diagnosing a beamline or diagnosing when a problem happened that I think it's worth thinking about using this. It's actually pretty old, and there's a lot of things I'd like to change about it with it, especially making the web page more modern and more dynamic, more usable. But it's already a fairly good thing to think about. And all it does is write data from PyEpics. It just sets up callbacks and writes data into a database. And then this application is reading the data from that database. So it's pretty simple from a PyEpics point of view, and it's very useful. And at our Beamline, we're monitoring something like 6,000 PVs full time. Most of them don't change very often, but we get, 200 changing every minute or so. And it's really useful to know when a motor moved or changed its direction or something. So for GUI controls, long ago, I started using wxPython. So there's a lot of code in PyEpics to help you write wxPython widgets and GUIs. So there are subclasses of many of the widget types, so plain text, a text control, an editable text string, an enum for a drop-down list, or buttons, or alarms, or floating points that you tie to a PV, so that when you update that text widget, it updates the PV. Or when that PV updates from some other source, that widget gets updated. And actually, much of this code was actually written by Angus Grattan, who was at ANU at the time. And so this is one simple example of a GUI code, but we're not going to be able to do any GUI programming in this class. It's hard to learn GUI programming in 2 hours. But those things are available if you're using it. And it turns out that for Qt, we're working on these, and we will work on more of them. And it's also somewhat easier. The subclassing of GUI widgets for Python epics is easier than with WX. OK, so here I'll show you some of the GUI apps that we have that you might be, again, this is partly, you might be interested in using them, you might be interested in modifying them, or you might get some ideas of the kinds of things you could do. So here's an area detector display. This is a ProSilica GIGI camera that's 4 megabyte camera. And we have this running in our beamline basically full time. This is to look at an image, and this just interfaces with area detector, and you can set, you can't really read those here. You might be able to read them from the PDF, but these interact with the exposure time and the color tables, and you can start and stop. And then these interact with the ROIs, so you can either zoom in on the plot or use the image overlay. So these are image overlays that are part of the area detector plugins. It's a bit slower than ImageJ, but it's as fast as the camera goes, actually. So it's good enough for what we use. So I showed the motor device, and one of the things that would be really helpful is if there was a nice motor widget that was sort of like the MEDM screen. We have this as well, too. So here's a list of a motor widget that looks a lot like the MEDM screen. And in fact, if you go to the More screen, you see this, which looks a lot like the debug page, or the all page, I forget. And this has, it's slightly easier to use because of you don't have to have the cursor in the box and hit the return and so on. You can enter values, the entry values can be only numbers. You can't make a mistake if you type a letter. It doesn't pop up an error box telling that you made an error just because you made an error. And the values indicate the soft limits. The tweak values, so the tweak values a drop-down list that's automatically generated based on the precision and range of the motor. And the More button leads to this panel. So similar to that, and based on that, we have a GUI. So this definitely is specific to my station and my beamline, and probably not of much use to you, but this is the kind of thing you can do. This is a smaller widget for operating 2 or 3 motors or more, and then when you give it you can type in a name here, hit return. It fills in that name, remembering these positions, and takes a picture either from a webcam or from an area detector. And it's simple. A simple INI file does a configuration for that. Also, we have a GUI for controlling and displaying XRF data. So this this is connected to a quad vortex XRF detector and shows the spectra here, and you get some nice widgets to interact and work with the data. So those are, again, things that if you're not using those applications already, or applications like that already, those are probably not of great interest to you. There's a StripChart, which might be of more useful or more general use. There's a StripChart application. I'll show you this. I'll do a demo of this if you're interested. But I want to talk about 2 other applications in the remaining time that actually I think you might actually want to use, or if you don't want to use them, I want to hear why not, because I think that these are generally useful. So Epics Instruments is a way to, with that, like that sample stage, to set up a group of PVs and be able to save the positions of them and recall and go back to those positions. So it lets you organize PVs into instruments, which is just a collection of PVs. And you can manage them. So here we have 8 instruments on this one frame that's tabs. So you can go back and forth between the different instruments. Each of them has something like 4 to 8 PVs. Most of them many of them are motors, so they're the full set of positions for the motors. And you can, each of the instruments you get to name, and it will remember all the settings that you type in a name for and return. simply typing a name in this box will save the position. And then clicking here and hitting go to will bring up a little widget to allow you to move back to that position. So this is useful for setting mirror positions or detector settings or so on. And the magic ingredient is to use a relational database, which is and using SQLite. So this program is then totally portable. In fact, we have this running. We have about 4 instances of this program working in our Beamline. Each user can have their own one of these and their own set of saved instruments and positions. On hitting go to, a little dialog box comes up that has the current value, the value that it will move to, and then you can click whether you want to move each one of those individually, or you can hit OK and drive all of them to the saved values. In editing an instrument, you can change what PVs are in that instrument or easily set a new instrument up. And I hope to be able to show you an example of running this. OK, in addition, this has a little server mode. So if that application is running, you can set it up to listen to a small EPICS record so that another process can say, move my sample stage or move the mirrors to silicon stripes, right? So you can easily, from another process or from another Python program, tell it to do a move to the instruments that you've defined, to the position names and the instruments that you've defined in this program. OK, so finally, I want to talk about step scanning, or scanning in general. Most of these are like step scanning, not necessarily limited to only step scans. So the step scan module provides tools like the EPICS scan record or spec to do simple scans from all within Python. So in here, you create a step scan, you add a positioner, you give it the range of positions, and then you can add detectors and counters and run the scan and write the data to a file. So this borrows many concepts from the scan record, but it's in pure Python. And it uses positioners and detectors and triggers much like the EPICS scan record. It's sort of closer to the EPICS scan record than to spec, but it has similarities to both. And this writes ASCII column files, and it expects the area detector to write its own data, which I think is the only viable solution and what everyone has adopted. So to do this, again, this borrows much from the EPICS scan record. There's positioners, triggers, and counters, and you can set those all up individually. You can also set up a detector, which encompasses a trigger and a set of counters. You can also record extra PVs, which is like the scan record. You can tell it at the beginning of each scan here's ring current and so on that you want to record. And there's methods that you can overwrite or define for what to do before and after the scan. It also uses the concept slightly different, is to use breakpoints as lists of where to pause and put out data. And that's so that you can do multidimensional scans without having scans looped. You just provide all of the data. You provide all of the positions that you would want to go to, and then tell it when to break for writing data out. Again, so I'll just say that again because it's a little confusing, I think. Positioners, there's an unlimited number of positioners you can use, and you provide the full array of points, not start, stop, step. And then multidimensional scans are not thought of as inner and outer, but you give the full range. So if you want to do a mesh scan, you have to provide the correct arrays for X and Y. That allows you, that's a little harder to do if you're doing a mesh scan, but it's not hard, right? Because in Python, that kind of thing is easy. But it also means that you don't have to do a mesh scan. You can do a scan of an arbitrary shape. So you could do a triangular scan, where as you increase X, you increase the number of points in the Y scan. And in addition, you can put in attenuators, filters, and so on at certain points. So you can have an array of positions. A positioner can be a very simple thing that puts in an attenuator every 10 steps or whatever. Detectors are also unlimited, and a counter can store any scalar PV. Actually, I have no waveforms yet, but in fact, I'm collecting some waveform PVs in this way now. I am collecting some waveforms. And it can definitely trigger an area detector to count to save its data. And again, there's already classes for scalars and MCAs and array detectors. And these detectors themselves add code for pre-scan and post-scan to set up the detectors into the right mode so that the scaler is in the right mode to be able to count. And for the MCA is in the right modes and so on. So then, built on top of that, there's code that's like the spec-like scan. So there's A-scan, A2 scan, all of these. And then the motors are simply any epics PV, although they're called motors. They're any epics PV. And the detectors, again, can be the scalars, MCAs, and so on, or area detectors. And this does not write a spec file. It writes a simple ASCII column file. I've tried to get a couple of people to help me with writing a spec file, because I know how it looks, and I know how to read one, but I don't know how to do it right. So, but if somebody's interested, it could be done. It's actually not hard. And this says on this, it says no live plotting yet on this, but I have some live plotting in other code that could be easily ported back to this. And again, this is built on top of the step scanning module. And you can also save, so here I'm adding positioners in the code here. You can do it as code or as an INI file. So also built on top of the step scan program code, there's some GUI code. And many beamlines want to provide a GUI for scanning, at least for simple scans, to their users, or even to use for the scientists. So here's a GUI for setting up line scans, mesh scans, actually slew scans, and XAF scans, where you set complex energy ranges. And there's a live viewer that plots the data as it goes. Actually, you hit start, and it will scan, and it will plot the data as it goes. This is a work in progress, and it needs a little bit more work, but most things are working. It needs some hardening by users actually working with it more than they have. And the way this works, actually, so you hit start, and it starts collecting the data. But the way this really works is somewhat more complicated, because really that GUI just puts a string of the scan parameters into a Postgres database. And then another process is watching that Postgres database, and that runs the scan, writing the data and posting the real-time data back into the database. And then this viewing application is reading from that database. So that means a couple of things. First of all, the clients can read the data from the database, but they don't have to be on the same machine. In fact, the server is on a different, so when I run that, the server and the client are on different machines. The database is on a different machine. But there could be multiple clients going at the same time. So you could have a web page as a client just monitoring what the scan is. I think that might be of interest to some people. And again, like SQLite or like using MySQL for the data collection in the archiver, a relational database really has a lot of advantages for these kinds of applications. Epics decouples already, sort of gives you the idea of decoupling a server and a client. In fact, all of this Python code is client code from the IOCs. The IOCs really run the motors, and we're just requesting that they be run. And Epics Channel Access gives you one way to talk between the client and the server. A relational database management system also gives you a way to talk between clients and servers. These are really designed for and very good at multiple simultaneous clients, data integrity and large amounts of data, and access security. So you have to log into the database. So you could have a login through a web page, and you could have remote access that's limited for a period of time or to certain clients. And they also allow multiple programming languages to write in to those databases. I don't know where that came from. Out of my mind, in mind. So the multiple programming languages, and the reason for that is that like channel access, it's a simple protocol. Relational databases also have a simple protocol for communication between clients and servers. It's called SQL. It's actually a very simple way to communicate and transfer data back and forth between client applications and server applications. If you can sit here for an hour and listen to learning channel access, you can learn SQL in like 10 minutes. It's okay, there's things about it that are really crazy, and the hard stuff gets really hard, but the easy stuff, like CA put and CA get, is really easy. Okay, so for the scanning application, what's next? Many of the things are working for this, but there's still more to do for the scanning application. And so now, my agenda, for standing up here for a couple hours is I'd really like to have some collaboration or ideas on this, on the scanning applications, on the instruments pages, on the web archives, because I think that those are useful for like pretty much everyone around the ring and possibly other beamlines at other facilities as well. I'd like to see ideas for, so I'd like to hear your suggestions or ideas, or even your collaboration, or think about why you might want to collaborate, or what you'd like to see for this, for either the scanning or the instruments or the web pages. So okay, so I think I'm done. This is the thanks page. Actually, there's a lot of people who helped with PyEpics and teaching me the hard parts of channel access, and also learned a lot about Python programming as I did this. So there's a lot of people to thank. They're all listed here. Angus Grattan from ANU, again, wrote a lot of the WX code. It's great. I'm very happy that happened. And we're going to work on Qt support, too. So, OK, so this is a good time to take a break, because the next thing we're going to do is to go through these exercises. And so again, there's exercises that are listed here. And there's 6 exercises that you should be able to do. And here's some information on what the PVs are. And we'll talk about these in more detail. But this is probably a good time for a break or for questions. OK, I'm done.